Well, good morning, everyone. Welcome to day 2 of our FRB Adventures this week. It's a great pleasure to chair this session, hosted 2 on populations, and also great honor to introduce our invited speaker to kick off the whole session this morning. Ziggy Pleunis is going to be telling us about a synthesis of those populations.
Thanks, Duncan. Thanks to the organizers for inviting me to give this review talk about FRB populations. I thought I'd start here with a little, I start here with saying what I'll present today is based on discussions with my group. I'm co-leading the Astroflash team at the University of Amsterdam and Astron. Some of us are here, and I'm also part of the CHIME FRB collaboration. I thought I'd start here with a bit of historical context. Let's talk about supernova for a little bit. Here's a report from Chinese astronomers reporting what we now know to be supernova 1054. And I think it's useful to look at supernovae and gamma ray bursts in the context of fast radio bursts, because what we once thought was one phenomenon, novae and supernova, we now know to be at least 3 different formation channels, making classical novae, thermonuclear supernovae, and core collapse supernovae. And also, when we look at gamma ray bursts, also once thought to be one phenomenon, it quickly turned out that there's short and long gamma ray bursts, which are made by 2 different physical processes. So who are we to think that fast radio bursts are just one physical phenomenon? And I actually think that there's also many, at least 2 different ways of making fast radio bursts. So I'm gonna try to see if I can remove this thing, because otherwise you can't see the titles. Let's see what happens when I press this. Okay, good. And I think the hide floating meeting controls here. Oh, no. Okay. Anyway, so to put all of this in context, I think we're all here to find the truth, to uncover the origins of fast radio bursts. We'd like to know what they are, how they're produced. And so I thought it's useful to put this into a little framework. First of all, we're trying to do systematic, large surveys to detect large statistical samples of fast radio bursts. We find gems in those large surveys, like the few % of sources that are so interesting that we can study them, and we can, in a lot of detail, we can learn a great deal about the population. We can build detailed models based on those gems. On the other hand, we'd like to characterize the selection functions of our surveys and our follow-up, which we can do through injections. Bringing all of this together, we can do population synthesis of the whole underlying astrophysical populations of fast radio bursts and fit that to our observed samples. So that's sort of the framework, and I'll go over the progress we made over the last few years and some ideas of what I think should be our next steps. So talking about systematic surveys. So I put surveys, this is just a 2-dimensional representation. I'll go in the next slide on some other axes, but you can look at the systematic surveys in terms of the rate of sources they detect per time and the localization precision. So an arc second gives you an association to a host galaxy. A tenth of an arc second unlocks the stellar population that the FRB is coming from. And then milli arc second gives you sort of the size scale for some redshifts of a supernova remnant or a pulsar wind nebula. So I put here sort of the first generation of FRB surveys with Parkes, Molonglo, VLA, and Westerbork. And then let's call the second generation of fast radio burst surveys. They moved a little bit more towards the top right, having been designed for larger source discovery rates and more localization precision. And we're now gearing up and hearing a lot at this conference about what I would call the 3rd generation then of FRB surveys. They're just sort of sitting here. And these large systematic surveys have given us great population overviews. So we've seen, for example, a sky distribution. On the top left, that's the updated one from HCRU with Parkes. Then there's the sky distribution from CHIME. There's a bunch of host galaxies from DSA 110, and then there's all of the dynamic spectra from the aperitif search of fast radio bursts. So there's a wealth of information in those populations. Now, the 2 axes I just showed is just telling part of the story. There's a lot of these surveys are complementary in different ways, and I'd like to highlight a couple of complementary niches. We're hearing more and more now about the nearby universe surveys that are uncovering the most nearby fast radio bursts that we can study in the most detail, and arguably there we can get the most multi-wavelength constraints. Then we have those surveys that are specifically targeting or sensitive to the high redshift FRB universe. So they allow us to study the source evolution with redshift, and they also give us the best constraints for cosmology studies. Then there's also those surveys that revisit the sky, like CHIME FRB scans the whole northern sky every day. We'll keep doing so even when Port is online. And there's those follow-up machines that can do systematic follow-up of other FRB discoveries to see if any of them repeat. And then lastly, there's those surveys at the lowest frequencies, like the MWA that we heard about yesterday, LOFAR that I work on, and in the future, SKLO, that are probing propagation effects of fast-faded burst. So lots of exciting things going on. And I think the next steps here should be that we should properly compare the all-sky rates of all of the different surveys to see, do the rates actually match up? Is there some evolution with frequency? Do we see different populations of fast-failure burst? From these large systematic surveys, we've gotten lots of physical insights in the origins of fast-failure burst. So on the one hand, we have energy distributions. This is from Ryan Shannon's paper on the ASCAP Craft sample. Then on the other, here's another example from a recent paper by Vishwan Shah, looking into the maximum energy of fast-failure bursts, looking at the CHIME catalog. We've learned a lot about host galaxy distributions. We can study the distribution of type and metallicity of galaxies. This is from Shotaro Yamasaki's paper, looking at the volume-limited sample. We can look at the offsets from the center. This is from Alexa Gordon's work, modeling the galaxies and then looking at the residual positions of the fast-failure bursts and seeing, are some FRBs more from the outskirts and some more from the centers of galaxies. And then another example is that we can, using the Faraday rotation, measure the magnetic field strength in the host galaxies of fast-failure bursts. So these are just some examples of how we can learn about the host galaxies of the fast-failure bursts. But the next step here is important. I think these are all mostly global host galaxy distributions of properties. And what we've learned, or maybe some of you have known this for a long time, is that the local environment properties are not necessarily correlated with the host galaxy. So what we really need to do in the next few years is zoom in further into the circumburst media of the fast-failure burst and uncover the stellar population and not so much the host galaxies. The other thing we get from large surveys is insights in cosmology and propagation effects. So one famous example is the DM redshift relationship or the Makar relationship. And this is an example from this beautiful work by Liam Connor et al. Looking at the extragalactic DM versus the redshift. So here we already were able to do a baryon decomposition of the universe using fast-failure bursts. But the next step here, I think, is quite obvious, is to interpret the spread in this relationship to probe fluctuations in the IGM and also learn about intervening halos. We've uncovered repeaters and some other subpopulations of fast-failure bursts. So repeaters represent about 2% of all fast-failure bursts, which we see in the CHIME sample, but seems consistent in the Mir trap sample. We see that repeaters have distinct burst properties, which are hard to reconcile with just having one source model or emission model. But so far, we haven't seen any distinct host galaxies if we compare the hosts of repeaters and non-repeaters. So there's still some work to do there. Next steps, I think, are to find more active repeaters that we can study in lots of detail, especially on the southern hemisphere. We don't have a lot of repeaters, but we do have a lot of really good follow-up instruments, so we should get on that. Then we also see that some repeaters are only active at a certain frequency, and we should really find more active repeaters at L-band so we can follow them up. And then finally, I showed Alexa's work on the galactocentric distributions of repeaters and non-repeaters, but this is really the next step. This will give us a lot of insight, and we can look back at the gamma ray burst history. This is a paper from Wenfei Fong looking at the HST data of many gamma ray burst hosts, and there you can clearly see the different populations of short and long gamma ray bursts. And I think we can make a similar plot for this for FRBs in the next few years. We've also found this new population of FRB PRS systems. Those are active repeaters that are all associated with a persistent radio source. You can see in the top right, for examples. I think what is one of the important characteristics is these are all compact on a few parsec scales, and that's one of the definitions, in my opinion, of FRB PRS systems. The other thing you see, if you look at the host galaxies, metallicity versus mass, you see all of those four systems are in low metallicity dwarf systems, which is quite peculiar. So you can come up with this emerging definition of FRB PRS system. And they're also in extreme magnetoionic environment as signaled by their dispersion and Faraday rotation. So we'd like to find out now, is this a evolutionary stage of repeaters? Is it an effect of the environment, or is this a distinct engine for fast failure burst sources? And the next steps here, I think, are also obvious. We want to follow up. We have a lot of PRS candidates in the literature. I provide some references, but we should follow them up at higher frequencies where we can get better angular resolution and with longer baselines to see if they're really compact at parsec scales and part of this population. And the other thing that would be really nice is to measure the PRS evolution over years, because at parsec scales are really probing sort of supernova remnant sizes, and if you can see if they really grow, that would be a major clue to the origin. Another subpopulation we uncovered is this subpopulation of hyperactive repeaters. They've been great for follow-up. On the one hand, we FAST has been able to constrain sort of the lowest energy burst from these FRBs to constrain emission physics. On the most energetic end, Omar gave a great talk about what we learned on that side. And then there's lots of really interesting spectropolarimetric follow-up with wideband receivers. Here's an example from Pavel Uterkar's paper, beautiful data set. And I think we'll learn much more from doing more of those kind of studies in the next few years. So that's the next step is definitely to look at more of these hyperactive repeaters with the new wideband receivers. So from the large surveys, we have lots of gems and well-studied sources. I think the ones on the top and on the right have had enough attention in the yesterday already, but I'd like to point out two more. So one thing you get from large surveys is also occasionally a very fortuitous line of sight. So this is one example where Kenzie Nimmo and I were able to measure two scintillation scales towards an FRB to really constrain the emission region to less than about 10,000 kilometers. And you need to be lucky to have this sort of setup and be able to do the measurement. So you need lots of sources. And I also encourage you to check out, again, maybe Wenky's talk from yesterday and Adam Dome's flash talk about this luminous sporadic radio pulsar that I think tells us something interesting about what could be the sources of some local FRBs. And the best example of a well-studied local source, I think, is still FRB 2018 or 916B, where this wealth of information from multi-wavelength follow-up really enabled us to make this coherent picture of what could be the model for this source. It looks to be a high-mass X-ray binary, and we need these kind of detailed models for individual nearby FRB sources to be able to extrapolate it to the extragalactic population. So that's the next step. Keep finding those few percent of very interesting sources, make detailed models, and then move on to modeling the population synthesis. So we do the surveys, but we want to know how effective the surveys are. And the way to do that is to do injections. This is an example from the Utmost injection paper. The idea is simple. You just run the regular FRB search, which you inject, as there in the top right. You inject fake signals, and you see how many of those do I recover. And this way you can learn about the selection effects of your pipeline. Here's an example from Utmost. If you look at the fluence and width, the injections analysis was able to uncover that the pipeline was not so sensitive to wide burst. And it's good that many, if not all, surveys now are doing these injections to characterize selection functions. We also need to understand the selection functions of our follow-up. And this is great work done by Bridget Anderson, looking at the selection function of path that we now regularly use to associate host galaxies with FRBs. And so from doing injections in path, Bridget was able to find that especially if you go to higher magnitudes or fainter host galaxies, there's a significant false positive fraction that we need to take into account. And so I think the next step in this case is really that we should revisit some of the associations in the literature that we've made in the past, maybe put a probability to them, and especially keep in mind that we now know that some FRBs are in dwarf galaxies, in globular clusters, or in satellite galaxies. So this may change the interpretation. Then the next step, the framework, the end goal, I think, is to do population synthesis to understand the true astrophysical population of fast radio bursts. So you can take your favorite model, you model the binary stellar evolution, You slap on the radio emission, which you should also model. This is an example from star-planet interactions. And then ideally, you also model the local environments and radio propagation in that local environment. And I think what we should aim towards is to then come up with these sort of rate calculations. Given your model, you want to be able to predict what's the volumetric rate per time of your model, and then we can compare that to the observed rates to get a percentage of FRBs that could be produced by your model. And looking at the literature, most of the theories, which have been really great, but they're sort of satisfied when they match the energetics, time scales, and the frequency scale. But to really compare it to the observed FRB rate, we need these rates. My dream, and I think the dream of many of us in the room, is to be able to come up with this pie chart in a few years to say this percentage of FRBs is coming from this progenitor and this from the different, which will also help us to figure out which sources are best as probes. And there's some examples of this already in the literature. This is much easier if your model contains white dwarfs, because the white dwarf rates in the universe are much better constrained due to various reasons. But we should work towards also being able to do this for neutron stars. We have amazing general purpose frameworks for population synthesis like FRB Poppy. We were able to model the repeat rates, and we've seen that just assuming, make some simple assumptions, we can see that the observations are consistent with all FRBs being repeaters, but I don't think that's the full story. We also need to model the DM and scattering of FRBs, and there's some examples of this as well. There's some ideas of there being a scattering horizon. If you go too far out into the universe, all of your FRBs will be scattered beyond detection. And lastly, we can also forward model our optical follow-up, and this is one example from a book paper by Jan Schiedler, looking at how much cosmology you get per follow-up time. And I think this is really necessary to improve our follow-up strategies. So the next step is really to connect our source models to the propagation effects and to organize our follow-up, especially in the era where we get like hundreds of posts per year around our shared physical goals. Just as a little bit of outlook, I'm almost there. Here's I've been talking about uncovering the origin of fast radio bursts, but we've heard about all these other source classes that we also like to understand. So there's the slow radio transients or long period transients. On the other hand, we haven't talked about the microsecond sky, but there might be a whole population of things there as well that we need to understand. And then now we're also starting to understand the rare radio transients, so the most energetic ones and the rare ones that we just need a lot of time on. And again, I was reminded of this phase space of supernova that shows a lot of similarities. So I'll leave you with this framework and my thoughts of what we should do next. And I'm happy to discuss either during the meeting or later. Thanks.
Thank you very much, Adam. Since we are very small, about number ratio of the and I remember the top one, the number ratio was about 4%. Now 2%. In this actually has the map or what by
Okay, for the people online, the question was about the repeater fraction in the CHIME catalog, which used to be 3 and is now about 2%. I think it's all consistent within the error bars, and there's no real sign that it's turning over.
Begin. Next, Adam, can you hear us?
Yes, I can. Should I share?
Yes, go ahead.
Okay. Uh,
We'll give you a warning, hopefully in the chat, this, 2 minutes to go.
okay, I'm having a little trouble hearing you, but can you hear me okay?
Yes,
Okay. And you can see my slides?
yes, we can see you.
All right.
Yeah, can you hear us now?
Yes. Yeah, you can see my slides?
No issues. Yeah, we're all good, you go.
Okay. Well, I will get started then. Hello, everyone. And I want to start by thanking the organizers for accepting my talk and allowing me to deliver it remotely. I do wish I could be there in person, but I guess that'll have to wait for another day. So today I'm going to be talking about the second catalog of host galaxies from the CHIME FRB Outriggers. As a quick outline, I'll start by discussing the data selection and VLBI processing stages, followed by how we search for probable host galaxies, and defer most of the discussion on optical follow-up to Alice Tsai's talk on Thursday. But I will give a quick hint of some of the science analyses that are currently underway with our sample, and then close by talking about how recent improvements in the Outrigger system address various weaknesses that have limited the host galaxy yield so far. So the CHIME FRB Outrigger network comprises 3 single-cylinder dish instruments spread across North America. The first of these is KKO, which forms the shortest baseline of 66 kilometers. The second at the Green Bank Observatory forms the longest baseline at 3,334 kilometers. And the third, most recent, in the Hat Creek Observatory of California, forms a 955-kilometer baseline, which is orthogonal to the CHIME GBO baseline. Each baseline constrains FRB positions along the baseline axis, such that in combination, we can get a 2-dimensional constraint without needing to fully image the fields. Outrigger Catalog 2 comprises observations from KKO and GBO only. So that's what I'll be talking about today. So the shorter baseline of KKO only allows for roughly 1 arcsecond of spatial resolution, which, as Ziggy hinted, is enough for host galaxy identification. But it does have the advantage that KKO and CHIME sightlines pass through roughly the same path to the ionosphere, so its impact is negligible. The much longer GBO baseline enables significantly higher angular resolution, tens of milliarcseconds, but it does require that we account for the ionosphere. Fortunately, we are able to fit for this as a residual dispersion between the 2 sites. And as shown by the figure on the upper right, these are our measured ionosphere differential tech values against the predictions of the international reference ionosphere. And we do see a pretty good agreement there. Some scatter is expected because one is a standard and the other is an actual measurement. The figure on the bottom right shows the KKO localization ellipse in orange compared with the GBO localization ellipse in blue for a single event. Another challenge with GBO is that we have many steady calibrator sources that are resolved out on the longer baseline, which makes it harder to phase reference. But nonetheless, a survey by Xion Andrew from 2024 found about 200 steady calibrators that are detectable with 100 millisecond integrations, which is better than we originally expected, which does allow us to do VLBI. So a timeline of the 2 catalogs. The vertical lines in this diagram mark the CHIME detected FRB events that resulted in triggers being sent to the Outriggers. Green lines mark events with successful VLBI reduction, and gold marks events that ended with a plausible host candidate. Our first catalog cut off at February 10th of 2024, and this new catalog cuts off at February 1st of 2025, just before Hat Creek turned on. So here's the breakdown of events through the VLBI analysis. In the time frame of OutCat 2, we had 566 triggers that were sent, resulting in data successfully written out at KKO, GBO, or both sites. The VLBI stage column here indicates for which baselines and events we were able to detect fringes on both the target and calibrator signal beams. And this ended up being the most significant filter in our data for both baselines, largely due to targets that were simply too faint to detect at the Outriggers or in cross-correlation. But for the events with detected fringes, the VLBI validation step, which looked for misidentified fringes and weaker detections, failed more often for GBO than for KKO due to a combination of factors, which I'll get to more later. Mainly, this is due to the sparseness and relative weakness of the calibrators, as well as a smaller band overlap between the 2 sites. We ended up with a full sample of 190 localizations. Most of these were from KKO, but 67 of them also included a GBO localization, and a further 14 were GBO localizations alone. We searched for candidate host galaxies in the Legacy Survey Data Release 9 and in Pan-STARRS Data Release 2 catalogs using the path framework to assign posterior probabilities to each galaxy in the field being the host. This framework uses the galaxy magnitude to calculate a chance coincidence probability, which is the prior on association, and then uses the localization ellipse as a likelihood. And overall unseen probabilities is also calculated based on the survey depth. Importantly, PATH does not use the FRB DM in its association, which ensures that our associations do not bias any inferences that we may wish to make about DM and redshift relations. So the two candidates in each field with the top posteriors are called the primary and the secondary, and we decide on which galaxies to schedule for follow-up based on these posteriors, getting spectra for both. We then classify our host galaxies based on these posteriors and their spectroscopic redshifts. So our two tiers of association are gold and silver, and showing an example of each in these columns. So the left here has a primary posterior or POX of 0.9, so that makes it gold. The right has a primary that's below 0.9, but the primary plus the secondary is above 0.9, and the spectroscopic redshifts are close together. So this shows that these are likely to be a multi-galaxy system. So even though we can't say confidently which galaxy is the host, we can confidently report the FRB's host redshift. So we call this one gold as well. The middle panel shows a case where the primary plus secondary is above 0.9, but the difference in redshift is a bit high, so we don't think they're associated. But since the primary is above 0.8, we call this a silver sample. And then we have a handful of hosts where we obtained a spectroscopic redshift, but the posterior, the primary was below 0.8, so we just call those our bronze sample. So altogether, we ended up with 65 sightlines with criteria qualifying for optical follow-up. Of these, we obtained redshifts for 42, and of those, 35 sightlines meet our gold criteria, and 7 are silver. And I'll reiterate, please stay tuned for Alice's talk to hear more about the follow-up results. So the number I want everyone to take away from this is that between this catalog and the first, from both gold and silver criteria, we have 54 FRB host galaxies from CHIME FRB Outriggers. So here are the extragalactic DMs versus redshifts, showing a nice linear Makar relation. The OutCat 2 sample, shown in red, extends a bit farther in redshift than the OutCat 1 hosts. And I'm sure many of you have probably already spotted the outlier right here. So I wanted to highlight this because it shows one of the limitations of our analysis. The path associated this FRB with this bright nearby galaxy, and intuitively we can look at this and see that the DM is a bit high to be consistent with this association. But this is what path deemed to be the most likely match. We're still kind of investigating what's happening here, but my interpretation is that this is a false association, which we expect for about 1% of our localizations, given some recent analysis by Bridget Anderson testing with simulations the false association probabilities of path. And since our sample concludes almost 200 bursts, it's not surprising that we get one. So with this new sample of host galaxies in combination with previously published results, several science projects are underway. As I've already mentioned a couple times, Alice Tsai is leading an analysis of the properties of the host galaxies in our sample, and we'll say more about that on Thursday. Rachel Darlinger, a PhD student at McGill University, is leading a statistical analysis of exploring how our DM versus redshift data can be used to specifically constrain galactic feedback by exploiting the sharp DM cliff feature in the DM redshift space, which we expect to be less sensitive to selection effects. Kenzie Nimmo at Northwestern is looking for correlations between FRB properties like scattering timescale and RM and the host galaxy properties, and is already finding some potential connections. Bridget Anderson, a postdoc at UC Santa Cruz, is using our sample to help to correct the path-induced bias in statistical measurements of galactocentric radii. And Leah Nagash, an undergraduate at MIT, has worked with me on modeling the DM contributions of galaxy groups in the foregrounds of our hosts. And there are several of our sightlines that pass through galaxy groups. So these projects are in various stages of completion, but I think we should all eagerly anticipate the results as they come out. Okay, so for the rest of my talk, I'm going to quickly go over the current state of the outriggers and how our recent developments address some weaknesses in our data reduction. As I showed before, we went from 566 triggers to a total of 54 bursts, which is not a terrific yield. There are three main filters in the data that cause this. So first, the oblong localization ellipses provided by KKO or GBO results in these ambiguous associations. So path only really yields a gold match above 0.9 about 20% of the time. Another significant factor is our RFI contamination. Despite being a radio quiet zone, Green Bank still sees some contamination at the bottom of the band, while KKO and CHIME are mostly missing the top of the band due to cell phone transmissions. We typically only get about 50% of the total band in cross correlation, which really reduces our SNR. And finally, on these longer baselines, we do have calibrators, but they are fewer and weaker, which can further lower our SNR. So the new outrigger at Hack Creek addresses the first issue. It's been operating since February 2025, and as of last week, has around 387 or data for 387 FRB candidates. It's probably changed since then. The HCO baseline combined with GBO gives us a 50 by 100 milliarcsecond localization region, which greatly increases the success of path associations. So the figures on the right are from an upcoming paper by Bridget Anderson, which I mentioned before, which uses simulations to show how different localization regions affect the success of path. And the full array localization ensures much more of our host associations have posteriors above 0.9 and greatly lowers our false negative and false positive rates. The results of the HCO commissioning process will be released soon in a paper being led by Matthias Lazda, a PhD student at U Toronto. To address the RFI contamination issue, we have an exciting new technique being developed by Shion Andrew from MIT and Juan Manapara from U Toronto. By constructing beamformer weights that maximize the SNR rather than the signal alone, and calculating this non-trivial noise covariance matrix, we can actually null out the RFI from the baseband data. So the figure on the right shows how this technique can quiet the noise in the highly contaminated LTE bands. This method depends on having good instrument gains, but can be applied to baseband data offline, promising to greatly improve our band coverage in the future. Another big factor in recovering our bandpass is in the complex gains used to calibrate the instruments. So the figure on the right here shows each colorful line is the system equivalent flux density for a single input at Hat Creek. The black line shows the median, and then the white lines show the SCFD for the full beamform response. And the RFI contamination across the band is affecting the complex gains used to generate this figure. But if through an improved RFI filtering process, flagging out those channels, and then using Gaussian process regression to fill in the gaps, we can obtain much smoother gains and reduce the apparent noise. And finally, to address the phase calibrator issue, we are implementing these real-time tracking beams at each outrigger site. This has been a long effort, but is finally coming to fruition. By saving the tracking beam data on each calibrator, allows us to make longer integrations without having to use up as much data storage, which not only increases the SNRs of our visibilities, but also gives us access to fainter calibrators that are closer to our targets, which will allow us to better account for the ionosphere. So to summarize, CHIME FRB outriggers now have 54 host galaxies we are confident in from just the first two outriggers. Several science projects are now underway, and significant developments over the last year have largely addressed the limitations that reduce the yield of the second catalog. So thank you all for your time, and I'll now take any questions you have.
I noticed that I noticed that the host galaxies are at 7.5. Do you think that's due to ambiguity or due to that nature of the host?
I'm sorry if I maybe if someone could put it in the chat, I seem to be having trouble hearing.
Hi, can you hear me? Hello, can you hear me?
A little bit, yeah.
Hi, I noticed that the host galaxies were less than redshift 0.5. I'm curious if that is due to localization ambiguity or due to the implicit nature of the FRBs.
I'm sorry, I still can't. Can somebody put the question in the chat of the Zoom call? Like I can.
We'll put it in the chat. Yeah. Does anyone else have a question or is that great? If not, then let's please keep on.
To talk about the FRB rate density of as a function of redshift using CHIME Catalog 2. So actually this work is ongoing in collaboration with these people presented in this here. Let me show this one. Oh, okay. Okay. Oh, no, I understand. Okay. And then I just want to remind Tomoki is going to give a presentation last day, and also Simon, collaborators, he's also presenting a poster behind. So then if you have time, please visit them. Okay, let me get started. It's really hard. Okay, so here I just summarize the selected the possible candidates for FRB progenitors. Maybe actually these are selected candidates, so there may be more than this. The problem is, so there are too many candidates for FRB progenitors. Then how can we constrain this possible progenitor FRBs? So this is one of the most important missions in astronomy, in the FRB science now. And then I would like to emphasize that actually the host galaxies has a very strong tool. It is a very strong tool to constrain the possible progenitor types of FRBs. And here I show two clear examples. So this particular FRB was found at the location of the globular cluster in M81 galaxy. Globular cluster is a very old population. So therefore, it is indicated that the FRB progenitor for this particular FRB is originated from old stellar population. On the other hand, this another FRB was located on spiral arm of this particular host galaxy. So therefore, this FRB might be related to the star forming activity or remnant of star formations. So therefore, these two examples really highlight the importance of investigating host galaxies. That's excellent. I would like to remind you that there is still limitations because number of identified host galaxies is still limited, So let's say that about 10% of F total FRB samples has identified host galaxies. So this number is actually far from the understanding of the whole sample of FRBs. So therefore, we need an independent approach to address the possible progenitor types of FRBs. To do so, in this work, we focus on the FRB rate density as a function of redshift, which allow us to use about 10 times more samples than before compared to previous studies. Let me explain this. I go back to that, this possible candidates for FRB progenitors. There are so many, but I want to remind you that we could, if I simplify the situation, we can separate these possible candidates into two different groups. The one is old object, which has giga-year timescale or giga-year lifetimes. And the number density of old object in the universe is related to the cosmic stellar mass density, because stellar mass in the universe is dominated by old objects in the universe. On the other hand, these young objects, they are most likely a remnant of star-forming activities. So they have a mega-year timescale. And also, they are expected to be related to the cosmic star formation radiation evolution, because they are remnants, supposed to be remnant of star-forming activity. So the point here is, this cosmic stellar mass density evolutions and cosmic star formation density evolutions are both well explored by galaxy surveys in the past. Actually, which is shown in this figure, a cosmic star formation density evolution is shown by blue line here, and cosmic stellar mass density evolution is shown by yellow line here. As you can see, cosmic stellar mass star formation density increases toward higher redshift until redshift about 2. But the cosmic stellar mass density evolution actually keep decreasing toward higher redshift. If FRBs originate from young objects, then naively speaking, number density or FRB rate density would follow the cosmic star formation density evolution. So therefore, FRB rate density would increase toward higher redshift until redshift about 2. If FRBs originate from old populations, the event rate of FRBs would decrease toward higher redshifts. So therefore, by investigating this redshift evolution of FRB rate density, we could strongly constrain the progenitor types. So this is the idea of this model. And here I can show one clear example from another type of explosions, which is long gamma ray burst. You know, long gamma ray burst is for sure related to star-forming activity because they explosion of massive star. And indeed, if you plot the rate density of long gamma ray burst as a function of redshift, it really indeed increases toward higher redshift, maybe up to redshift 2. And this increasing trend is well synchronized with cosmic star formation density evolution, which is shown by here. So therefore, my question is very simple here. What is the FRB version of this figure? So which could constrain the FRB project types? Let me try to analyze this. And actually, there are two different approaches to this kind of subject. One is model-dependent methods. In this way, so you assume a certain shape of reduced evolution of this different rates, assuming this cosmic function evolution or cosmic stellar mass evolution with a parameter of alpha. And after constructing this model, you can fit the model to the observed distribution of dn or fluids. So this is a model-dependent approach. But my point is, this redshift evolution part is the most key point to address this approach of the types. So therefore, I don't want to make any assumption on this redshift evolution part. Therefore, I try to adapt this second method, which is the model-independent method. This is called Emax method. So this is very commonly used for extragalactic astronomy, say luminosity functions for galaxies or functions of quasars, blah, blah, blah. And the point of this method is we can directly measure the FRB rate density as a function of redshift without any assuming function shape of the distribution. Okay. And then this is the quick summary of previous works from this subject. Based on these two approaches and also different FRB catalogs, I think many people try to understand this cosmic evolution. However, I would say the point is, so far there is no conclusive answer, I believe. That's maybe fair to say. So therefore, in this one, we use the CHIME catalog tool, which includes more than 1,000 FRBs. Then, here is the sample selection in this one. I have so many selection criteria here. The basic idea is we try to select the FRBs for which we will know the selection functions, dimensional bias. And by applying this selection function as selection criteria, we selected more than 1,000 non-leading, which is actually 10 times more samples than my previous work. Okay, let me show one example. I'm sorry to showing this preliminary result. But by doing this Bmax method, we can calculate the FRB rate density as a function of energy B. And the different color corresponds to different redshift, which are derived from Dn. And then, as you can see, actually, we can see this redshift evolution of energy functions. And by integrating this energy function, actually, we can calculate the FRB rate density for each redshift B. Then we get this result. This is y-axis with the FRB rate density as a function of redshift in x-axis. Our measurement is shown by red stars. And then our preliminary result is the rate density decreases toward higher redshift. And then this decreasing trend is consistent with the cosmic stellar mass density evolution. Therefore, this may suggest the majority of non-repeating samples from CHIME 2 originated from all stellar populations. Maybe. But I have some caveats. Let me discuss some caveats. The one important point is frequency domain. Actually, when we compare different redshifts, observed rest frame frequency is actually different. So then, as you can see, this is the peak frequency or the source plane as a function of redshift direction Dn. And then there are so many FRBs at lower frequency here. But this kind of low frequency population at low redshift cannot be observed at higher redshift because of the limited bandwidth. So therefore, actually when we compare different redshifts, we are comparing different rest frame regimes. So this is maybe need to be understood. Indeed, actually we plot a histogram at all redshift Bs. Actually low frequency FRB population is more than higher frequency. So therefore, this could be either intrinsic or either observational bias. But anyway, this effect needs to be addressed in order to precisely measure the cosmic evolution of FRB. Okay, let me conclude my points. I use the CHIME Catalog 2 to investigate FRB rate density as a function of redshift, and using 10 times more samples than before. And then rate density seems to be decreasing toward higher redshift. This may suggest all those stellar populations, but I think we need to address this frequency domain problem. And also, I think we need to also make sure this my work is all based on DM generated redshift. So therefore, I think it's better to make sure that for high DM sources are really high resolution or not. Okay, I finish my talk. Sometimes.
Thank you very much. Questions?
So your question is also how I use selection function by hiding samples.
Yes, I will think of the most events higher.
So in my calculation, I just simply based on selection function derived from CHIME Catalog 1 at this moment. So then, as far as I know, I include the selection function in CHIME Catalog 1 is for DM, selection function for DM, and duration, and scattering, and fluence. I included all these four selection functions, but it is not particularly for redshift. Maybe redshift effect could be included in DM selection function, I guess. I'm not sure if it's answered your question. But you can press like Exactly. In my study, actually, this kind of analysis is out of the platform. Therefore, I didn't really think about this in my analysis. I use only the platform is not the platform.
I see. Thank you very much. Actually, I see good manifestation of the two marks. Yeah, I think right away, this next step, maybe we should consider the two marks. Say, for example, in my case, now we can believe it's a decreasing trend. And then now actually we still see some delay or deviation in the year one of the point. And maybe next step, if we can verify our measurements, then the next step will be we can tune this data to be the model to match the design of the data. Then we may be able to derive the data. That's maybe the step. Thank you very much. Okay, we can move on. So let's take a speaker again. So next, still consistent populations over time, non-consistent FRBs, by backward non-parametric versus increases for population. Thank you.
So good morning, everyone. My name is Ziliang Zhang from the Hong Kong Institute for Astronomy and Astrophysics. Okay. So I'm very happy to have this chance to share our recent work about constraining the CHIME, the non-repeating FRB CHIME population. So here's the outline of my talk. And thanks to the previous speaker, especially Hashimoto, I can save a lot of time for the okay, really speaking. Okay, that's much better. Okay, and so we mainly use like two independent methods in this work. First is a backward non-parametric method which means that the really from the observation observable, the dispersion measure, the fluence, we want to reconstruct what the intrinsic redshift distribution and the energy distribution looks like. After getting this marginal distribution, we also want to test whether this two marginal distribution is independent or not. And finally, we use the forward independent forward population synthesis, starting from some assumption. And we for different theoretical model, we can have a prediction distribution and compare it with the observation to see which model can reproduce observation. So we can skip this introduction. And the motivation is very simple. So we have many host galaxy observation, but this is very limited sample size. And they are for many different telescopes. We have strong selection function and it's highly heterogeneous. So thanks to CHIME, we have a more uniform sample sets and mainly focus on this redshift distribution. So I just show it in a linear scale. So there are two types of transition. One is that this transition will follow the cosmic star formation history very well for the known or progenitor like the co-collapse supernovae or the long gamma ray bursts. Another type is the delay distribution. This is corresponding to like compact binary mergers. One is a supernovae. It takes very long time from their born to their finally this phenomenon or the burst happen. So the points of using CHIME is that you have a much uniform homogeneous sample size, but you still need to consider this selection effect. Here is their latest result of the selection effect. There's a scattering timescale influence and possibilities and dispersion, but all these will affect the detection probability. So it's a highly non-trivial selection function. Another very important issue is that because the localization, the CHIME reporting intensive fluence is only the lower limit of the true physical fluence. So they calculate for the same event, the fluence calculated from the baseband data is much higher than the intensity fluence, and this factor can be like 3 or 1,000 times. Another is that because we don't have the redshift measure. So we can only use the dispersion measure to estimate or use a distant posit. And the mapping from the dispersion measure to the redshifts is not a one-to-one mapping. There's a large uncertainty here. So what we do is use a backward non-parametric method. There's the older version, which this method means is that for each event in this space, you can construct compare sets, and within these compare sets, you can the ratio of the event within this redshift interval over the whole the all event within this rectangular. This ratio is proportional or equal to what this ratio in the intrinsic space. So, but this previous study, they haven't considered the selection effect here. As you can see, this color bar shows you at different position, you have different detection probability, and we include this detection probability of the selection function into account. And here you can calculate this effect. So here is the result. So for each event in the catalog, we assign a redshift and a baseband fluence based on the empirical relation, and we generate many categorization. For each this categorization, we apply the weighting method, and here it shows you the marginal redshift distribution. The upper panel is the cumulative distribution, and the result is showing in this grid solid lines, and they compose it like an uncertainty region. You can see that all these results give you there's delay with respect to the cosmic star formation history that the green dashed line, and we can show it in the probability density place. And we also get the marginal energy distribution. The power index is around -1.8, consistent with previous result. We also test this method to the baseband catalog, and we also consider if there is a spectral index varying. So our result is that unless this spectral index is very extreme, this result is still consistent with the current result. So after getting this marginal redshift distribution, but we don't know what their joint distribution looks like. As here, I show you two extreme examples. The same marginal distribution can respond into very different joint distribution. So we want to test whether the redshift distribution and energy distribution is independent or not. So here is how we test this. We under the assumption of independence, we generate some sample and compare the mock event with the observation. As you can see here, all these correlation coefficients shows you they are overlapped, which means there's no strong deviation between the redshift distribution and the energy distribution. And finally, we use formal population synthesis, which is independent. And starting from some theoretical model, we generate some mock sample, pass them to the selection effect, and to see the final observable, like the fluence and the DM, whether this theoretical model can reproduce the observation result. As you can see here, with the star formation history model still cannot reproduce the observation distribution. So for the time, because of the time, I just give the summary here. Okay.
So there are some selection effects that are equivalent on, like how many of the FRBs together. We've seen some evidence that people are discovering very long gathering time of order a second in some FRBs, which would mean most of them would be livable by time. Did you look at gathering at all, and how did you model what you do?
Well, because the scattering in the CHIME is also quite complicated. So we just cut the very highly scattered events. I'm not pretty sure how this will affect the node, but
right. I was just curious, are you using the regular selection function in your analysis? Is that?
Yeah. The length is 4-dimensional solution.
So I think that doesn't include scattering. Yeah.
they included the scattering for the less scattering events, but
There's some limits to that.
Yeah, I said limits. Yeah.
Okay, let's thank you. How we constrain the delay time distribution methodologies using practicals.
All right, hello everyone. My name is Alexa Gordon. Over the last 6 years, I've been a grad student at Northwestern. I'm happy to say as of 2 weeks ago, I'm no longer a grad student. And we'll be starting, thank you. I'll be starting as a Brinson Prize postdoctoral fellow at Caltech in a couple of weeks. So today I'm happy to present some preliminary ongoing work into the delay time distribution of FRBs. And of course, this work is done in collaboration with the wonderful people of the CRAFT and F4 collaborations. All right, so first off, what is a DTD? So before talking about distributions, let's talk about delay times. So generally, the delay time is the time between the progenitor's birth and when the transient occurs. So if we think about this in the context of FRBs, assuming a magnetar progenitor, in the prompt case, the types of stars that go core-collapse supernova to lead magnetars live for a few to tens of meg-years on the main sequence. Your magnetar is active for a few kiloyears, and at some point, we'll see an FRB go off in a host galaxy at some redshift. In the case of a more delayed formation channel, such as the merger of two white dwarfs producing your magnetar, these types of stars live for hundreds of meg-years to a few giga-years. You need some extra time for your dynamics to merge those, and then the track continues on. So the delay time distribution encompasses all of these individual delay times across the entire population. So if you have 70% prompt, 30% delayed, it all shows up in the general DTD. So why is this useful? Ultimately, the delay time distribution tells you about progenitor evolutionary timescales and formation channels across the population. So to give a couple examples from other transients, in the case of core-collapse supernovae, the death of massive stars, their delay time distribution traces cosmic star formation very closely. But short gamma ray bursts, which are generally the merger of two neutron stars, these systems take much longer to form, and that also shows up in the DTD with a very long delay tail. So how do you go about measuring a delay time distribution? There's a couple ways to do it. The way I'm doing it, I call the redshift method. So I have this flow chart here of how you could form an FRB, assuming they come from magnetars. We understand the first part of this pretty well, so we can use the cosmic star formation rate density, SFRD, which broadly tells you when star formation is occurring in the universe. And we also know the end state pretty well, so we have our observed redshift distribution. For this analysis, I'm using FRBs from the CRAFT sample, as it is a large, very complete sample and very representative of the total FRB population. The middle bit, of course, is what we don't know, but there is one complicating factor. You need to account for your telescope selection effects. This is all incorporated within the ZDM framework developed by Clancy James and collaborators. So this becomes a problem of we have 3 knowns and 1 unknown, so you want to rearrange for it and solve for the unknown. So essentially, I'm trying to figure out what functional form delay time distribution do you need to reproduce the observed redshift distribution of FRBs. So I first wanted to ask, do FRBs even need a delay? Or is the observed redshift distribution just the product of selection effects on the SFRD. So if the answer is no, then FRB progenitors trace star formation directly and follow prompt formation channels. But if the answer is yes, then at least some fraction of FRB progenitors require delayed formation channels. So to do this, I first need a sample of, or a synthesized population of FRBs that perfectly trace cosmic star formation as seen by Kraft. And that is what this plot is showing you. So I'm using the ZDM framework to synthesize these. This is a plot of extragalactic DM versus redshift, essentially a probability map of the types of FRBs you would expect to see if they're perfectly tracing star formation. So here's what that looks like in CDF space of redshift. So the pink curve is just pulling out from this figure here. In green, I'm also showing the star formation rate density to highlight the importance of accounting for your telescope selection effects. ASCAP is not observing the entirety of the SFRD. The pink version is our version of that. So how do the observed FRBs compare? I'm now showing that in black here. So these are 44 FRBs from the ICS sample, and you can see these two CDFs do not agree. 97% of the time, Anderson-Darling tests are saying these distributions are statistically inconsistent, meaning FRBs require a delay. But I have an asterisk there, because you might be asking, and if not, you should ask, is this a fair comparison? Is that really all of the FRBs? So the 44 that I'm showing are all the ICS FRBs we have spectroscopic redshifts for, but we're missing 10 of them. I'm working on it, but some of these ones are really difficult. So to test the question of, is this apparent delay just an observational bias of these 10 that we're missing? I used the McCart relation to infer their redshift given the DM, throw them in the CDF, and do this comparison. So here's how that looks. So the CDF on the left I was showing before, this is the 44 spectroscopic sample, and on the right is including those 10 FRBs that we don't have the spectroscopic redshifts for. And what you can see is it does a lot better at the high redshift tail, but the median is still really bad. These distributions are not agreeing. So I want to just emphasize here, this is now a complete representative sample of FRBs. So given the distinction, you can make the statement that the full Kraft FRB population is inconsistent with a population of FRBs that directly traces star formation. So to answer the question, do FRBs require a delay? Yes. Then, of course, the next step is to figure out what it is. So this project is currently ongoing. I'm going to show some results of using a power law delay time distribution. There's several more on my list to test. This is just the first one. So here's a PDF of 3 different power laws. The main knobs you can turn are the minimum delay time, maximum delay time, and the power law index. So this is just varying 3 different power law indices. Why power law? It's been explored before in the FRB literature from the DSA team. It's a very common delay time form. It's easy to parameterize, but there's not really a theoretical motivation for why FRBs should follow a power law. Nevertheless, it's a good first place to start. So what I did is used the synthetic population of FRBs that perfectly trace star formation, added in a power law delay time distribution, and here's the resulting CDFs. So in black again, these are the 44 spectroscopic sample. There's the SFRD in green for comparison. And then these 3 CDFs in purple and blue are the power law delayed population, just changing the power law index. So in general, the inclusion of the delay time distribution is shifting to lower redshifts into better agreement with the FRBs. So what I find is that the observed FRBs are more consistent with the shallower power law indices or longer T-mins. So this means that there's longer delay times that are preferred in the population. And instead of showing you yet more CDFs, I will just say this also holds when you account for those 10 that we don't have the spectroscopic redshifts for. So I mentioned this is preliminary. The next phase of this analysis is to fit directly for the delay time parameters using an MCMC likelihood analysis and also testing other delay time distributions. So I'm going to try things that are similar to quark-lap supernovae, similar to how you would find FRBs in globular clusters, and also combinations of delay time forms to hopefully constrain the fraction both of prompt and delayed channels. So as this is ongoing, I'm not going to draw any strong conclusions at the moment, but I will leave you with this. That what I'm finding is that at least some fraction of the FRB population does not directly treat star formation, even when you account for these ones without redshifts. And more work, of course, is to come to quantify the fraction, the degree of the delay, and ultimately what it means for the progenitor and formation channels. So with that, I'll end, and I'm happy to take questions. Thank you. Yeah, it's a good question. So just to repeat for online, what do the host galaxies look like for the sample? I've not done a detailed analysis of all 44, but a lot of these do overlap with some of my previous samples, and they're broadly star-forming galaxies, spiral galaxies. We're not seeing like an overabundance of massive elliptical galaxies that would point to a delayed population. So a good amount of these are coming from just typical star-forming FRB hosts. I think the bias would solely come from, do we know the redshift or not? And we do have the redshift for most of these. The ones that we don't have redshifts for, it's largely just a product of not having observing time. So I think we do understand the optical bias pretty well. Mm-hmm.
All this today, what would be the parameters that we have practitioner and FRBs are currently so we mentioned, for example, as one figure of Chinese so I will initially try this and how do you allow using the data constraint and forming the data. So we not be problem
yeah, thanks for that.
Okay, I think we should move on to our last speaker. Let's thank Alex again.
Yeah, hello everyone. I'm Songbo, currently working for Purple Mountain Observatory, and today it's my pleasure to introduce some of our recent work about the process. But I also come from the fast reverse because I spend most of my time to studying the fast reverse, but currently I just working on process and we get some new idea for fast reverse. So I will say FRB, arrays, and neutron stars. Okay, for me, there are only two direct close for FRB origins. One is come from the galactic magnetar, it's come from the Guiyang magnetar, and another come from the global clusters. That's why it indicates some ancient stars. But I think both of them indicate that the FRB origin can be related to the neutron stars. So if it's related to neutron stars, we know the neutron stars can have already be studied for more than 15 years. And the the single pulses come from the pulses could be quite stable, but sometimes their time can be extreme variable. We'll say come from the pulsar, the non-linear pulsar, and extreme non-linear pulsar, and to the arrays. But for most understanding is the pulsars, single pulses, their fluence, flux, and the width is relative stable. So we try to build a database of the single pulses, and we contain single pulses come from 363 pulsars. We study their fluence ratio. All the single pulses detected by one telescope, and you can see the fluence ratio can we built a ratio 10, and most of them below 10, and for one telescope, the maximum fluence ratio is 175. But that's the observation from some old data. If you use some new data, this is the RS from the first observation, and you can see the single pulses could be quite variable. And also the pulse shape just changed, and the fluence ratio is also more similar to the FRBs. And for this source, the fluence contract can be up to 1,000. And we will say most of the FRB are one-off. So can RS be one-off? We're studying, actually I do discover 5 so-called one-off arrays, and we study all the fast parks archive, and we pick out there are around 10 arrays have already been followed up for many hours, but they didn't detect any repeaters. So then we mean this source. This is the SCAP source. The DM is only 4, and it's really bright. It's up to 1K Yang-CG millisecond. And this source can be observing by fast. So I think for this source is my best chance to detect rainy one-off array. So we try to follow this source by fast, and we say it's a pit, and it can be really faint by fast. It's even close to the fast sensitivity detection. And we do detect this source by PAX. It's kind of narrow band. It's only appear in a very narrow band. And we try to give a distribution of the fluence is up to 5 magnitude distributions. And we can detect this source by the ADCA 10-second time resolution. So the pulses of this source can be up to 3 Yang-CG millisecond, and from fast it can be below 10 Yang-CG millisecond. So it's really a variable arrays, and this is not unknown. We get another one. So at one time, SCAP detect one arrays, and then we know it's really bright at SCAP time, and then we realize this may be an old source from the LSable, because LSable do report a marginal detection for similar position, and we are not sure if the SCAP, because the LSable only detected one marginal. So, and now we have cracked one arc-second localization, and this source can also be observing by fast. So we do observing the source by fast, and the situation is similar. The fast can detect the source at really faint single pulses, and the structure can be really variable, and the middle single pulses, the width is about 1 millisecond, and the widest pulse we detect is more than 100 millisecond. And from PAX observation, we see already strong scintillation. So we think of this. So why this source can be quite strange? So we just go through all the single pulses for all the known single pulses emitter. We pick out 3 pulses. One general pulsar, the Kraber, the 2 RS. By the way, I forgot to say that the DM4 source seems to be the binary. We just time it, and also the magneta, the galactic magneta. Even we exclude the famous FRB burst. This source also detects some bright pulses, not that bright, but still bright. So the fluence ratio is also up to 3 magnitude. So we just think of, we can try to define a new population. We give a definition is the detect single pulses with fluence contractor above 3 magnitude, it can't be explained by some scintillation. So it could be something, but I think this definition is quite fair because fluence won't be affected by any, such as the time neutron or something others. So we'll see the source and we try to report this source, and we think this kind of source will be hardly affected by telescope. You can only detect this kind of source by different telescope, and you can give a real fluence contract. So we'll say the telescope with extreme variable sensitivity can discover this kind of sources, and we think these sources can be more than 1,000 in current, in the future. Okay, that's all my talk today. Yeah, that's what I'm saying. I think if you use a small dish and you're waiting infinite time, you can detect much bright pulse from some known sources. And if you have some telescope, such as 1 or 2 magnitude more sensitive and fast, you can detect much fainter pulses. Even for our 2 sources, it should be more faint pulses, but we can't. Yeah. Yeah, the DF4 sources, we just get enough TOA from fast observations, and we see the peak seems to be smaller and smaller now, and we try to combine the data, and but the orbit constraint is very bad now, so we can't. But I think only Barry can explain that. Yeah, and the Russians have to check the data now, so I didn't show any plot. But I think we will give some results very soon.
Okay, well, let's thank the speaker again. Thank you all.